we are talking about temperature, heat. Last time we started talking about the ideal gas law. So we're going to do a little bit more practice with the ideal gas law today. And then we're going to kind of move into a little bit more physicsy stuff, a little bit less chemistry. So let's review what the ideal gas law is. It says that the pressure times the volume equals the number of moles times the ideal gas constant times T. So a few things to remember. The value of the ideal gas constant that we use in this class R equals 8.31 joules per mole Kelvin. This one is designed assuming that we're doing our pressure in pascals and our volume in cubic meters. So, you know, we have to make sure if we're just using the ideal gas law once, like we know the, I don't know, the pressure, the volume, and the number of moles, we want to find the temperature, then we better make sure we have pascals and cubic meters. But when we're doing, comparing the conditions at one point in time to another point in time, then we typically will divide the ideal gas law by itself. You know, P1 V1 equals nRT1 divided by P2 V2 equals nRT2. When we do that division, that ratio kind of thing, then the units aren't so critical because our units are typically all going to cancel out anyway. Okay. The second thing to keep in mind is that the temperature better be Kelvin because this does not have a delta T in it. And it wouldn't make sense if we had a negative temperature in this formula because that would mean a negative pressure or volume. So I know a lot of people are, you know, have seen this somewhere before, and some people, few people haven't seen it before. So it's okay either way. But in physics, we actually tend to write this equation a little differently. This is how chemistry classes do it. They like to measure how much gas you have with N, the number of moles. Yeah, Lauren, you have a question?
Yeah, I just had a question about the units, what you were talking about. So when you're doing the volume, this formula said it has to be in cubic meters. So what was the conversion exactly? Like the conversion to the, like we were given liters and milliliters, because that's what it does like with most of the homework.
Yeah, so 1,000 liters is 1 cubic meter. So it's basically, you know, divide your liters by 1,000 to get the cubic meters. And we're going to have a lot of examples of doing that as we go. Okay, so in physics, though, we don't generally use this number of moles. That seems like a weird thing that chemists made, and we need to count how much stuff. But in physics, we like to write it a little differently, and we'll probably kind of use these 50-50. We write it in terms of N, the total number of particles. So I guess the reason chemists use number of moles is because the number capital N is a very big number usually. I mean, you take a, you know, I don't know, a tank full of a gas, and there's 10 to the 23 or 24 or 25, you know, particles in there. So they kind of break it down into numbers of moles. But otherwise, it's the same equation, but because we do kind of different, instead of moles, we do number of particles, we need a different constant in the equation. So that constant is a K with a little b on it, and that's called the Boltzmann, or Boltzmann's constant. So again, this is just basically doing slightly different units. The connection is as follows. It should be that the number of particles times the Boltzmann's constant should be equal to the number of moles times the ideal gas constant. So how do you find the number of particles if you have the number of moles? You just, the number of particles is just the number of moles times what's known as Avogadro's number. And again, if you've had chemistry, you've seen this before, but if you haven't, it's just the number of particles in 1 mole. Okay, so it's kind of like if we were counting things by dozens, and little n was the number of dozens, and big N is how many total eggs we have, we would just take the number of dozens and multiply by how many eggs in a dozen. So here we have, 1 mole is, the Avogadro's number is 6.02 times 10 to the 23rd particles. So it doesn't really matter if we count them in dozens or gross or anything. The chemists like this number, 6.02 times 10 to the 23rd. So what that means then is that the physics version of doing it, if we replace the number of particles by number of moles times Avogadro's number, we can see exactly what this K Boltzmann is. It's K Boltzmann is really just the ideal gas constant divided by Avogadro's number. So it turns out to be 1.38 times 10 to the negative 23 joules per Kelvin. So again, you don't have to memorize these numbers. Those are just given to you on your equation sheets when you do a contest. But we kind of need to be able to do both approaches. So when we're talking about kind of microscopic physics and how the pressure is related to like individual particles bouncing around, then we need to use the physics version. And if we just want to know, I've got like 3 liters of gas and I heat it up and I want to know how many liters of gas I have now, then the chemistry version is just as good. Okay. Any questions about those constants? All right, let's just do a little bit of practice with the ideal gas law. So we're going to use the college physics book. And this is just problem 16.1. We can let's use the physics version of the ideal gas law this time, just to see what, how that's different. Maybe I'll show you both ways. It says a mass of oxygen occupies 0.2 meters cubed. So I know that that is the volume because of the unit, 0.02 cubic meters. At atmospheric pressure, and then they kindly tell us that that is 101 kilopascals. So I don't want kilopascals. I'm going to change that into, I know that it's 1.013 times 10 to the 5th pascals. They kind of left the 3 off. I'm just going to put it back in there. And 5 degrees C. So the temperature equals 5 degrees C, but we don't want C, right? I know we want Kelvin. So does anyone remember how to get Kelvin if we have Celsius?
Add 273.
Yeah, we add 273. So that's going to be 278 Kelvin.
Did I sound better that time?
What's that?
Did I sound better that time, or is it still?
Yeah, it was clear.
Okay.
Yeah.
I was saying it is already snowing where I'm at.
Oh, where are you?
Chesterfield Creve Coeur area. It looks
Oh,
like it's
yeah?
kind of stopped, but it's like, yeah, it's definitely like slushy, sleety, snowy, gross. Anyway, back to it.
That's good to know. My wife is out of town this weekend, and she just called me like an hour ago, and she said, "You gotta go bring my plants inside." She put all of her like big tropical type of plants outside to let them get sun, and then she, heard that it's gonna snow, and I was like, "It's not gonna really snow." So I actually brought them in. I'm glad though, because I'd be kind of in deep water if I didn't do that. Okay. So this says determine its volume if its pressure is increased to 108 kilopascals. So this is going to be volume 1, pressure 1, and temperature 1. And we want to know volume 2 if the pressure 2 is 108 kilopascals, which is going to be 1.08 times 10 to the 5th pascals, while its temperature is changed to 30 degrees C. So the temperature 2 is 30 degrees C, which is going to be, well, if we add 273 to that, that's going to be 303 Kelvin. Okay, so we want to do the ideal gas law, and anytime, not anytime, every time that we know the condition of a gas at one time, and then we want to find out what happens at another time, or one place and find out what happens in another place, we just simply write the ideal gas law twice. PV equals, we could write the chemistry version or the physics version. I'll show you both ways so you can see that it doesn't really matter. We write it twice. And we just put ones on one of the equations and twos on the other one. Since what I'm looking for has a 2, I'm going to put the 2's on top. So P2 V2 equals NR T2, and P1 V1 equals NR T1. And then we just divide these equations. And I'll do the same thing for the physics version and divide them. And we can see when we divide them, the little n and the r on the chemistry version cancel out. And on the physics version, the big N and the K Boltzmann cancel out. And it really doesn't matter which version we're using. Okay, it's going to be the same either way. So I put the 2's on the top because I'm just thinking ahead to the algebra that I have to do. What do I have to do? I have to rearrange this whole thing and solve for V2. And if V2 were in the denominator, that would just be like an extra step for me. So just, you don't have to, you could put the 1's on top and it's just going to be one more algebra step. So what do I do here? Now you may notice the solution's going like this sometimes. P1 V1 over T1 equals P2 V2 over T2. I would say don't do that. Okay, that's kind of what we get from the ideal gas law, but it's not always the right thing to do. And furthermore, it makes it feel like every time you solve the problem, you got to remember it will do this. Sometimes I use this, and sometimes I'm going to use P1 V1 equals P2 V2. They just kind of use these different equations. And I don't think it's beneficial to have a whole bunch of different equations that you have to decide, what do I, which one should I use in this case, and which one should I use in that case. We should just have one equation, which is the ideal gas law, and it's always going to work. Okay, so I really recommend that you follow the approach that I'm doing here. And ignore what they do in the solutions. Because if you look at the solutions, it's going to look like every problem you have to come up with a different way of solving it, when really it should be the same way every single time. So what do I do now to solve for V2? I'm just going to move stuff to the other side. So this, P1 and V1, I'm going to multiply it over to the other side. And this P2, I'm going to divide it to the other side. So what we wind up with is V2 equals P1 V1 times T2 on top, and on the bottom I'm going to have P2 times T1. And that's basically it. Now I just plug in my numbers. So I changed things to pascals, but we could have kept them in kilopascals because those units would have canceled anyway. But we'll use pascals. We have 1.013 times 10 to the fifth, because you can never go wrong if you put them in pascals, times the V1, which is 0.02 cubic meters, times the T2. Now, you could not get away with keeping the temperature Celsius because 30 over 5 is not the same as 303 over 278. Those do not give you the same thing. But for the units of the pressures, we could do that. For P2, we have 1.08 times 10 to the fifth. And my T1 is 278. So all of that times 10 to the fifth stuff just cancels out. And my temperatures, technically we should have Kelvin on these two temperatures, but those Kelvin are going to cancel out, and it's just going to leave me with cubic meters. But let's work out how many cubic meters. It did not work out. We'll try it again. There we go, 0.0204. If we were doing this in liters, then we could keep it in liters and just have our answer in liters. It would be 20 liters would become 20.4 liters. So even though it looks like that 4 doesn't matter so much, that's like half a liter. That's a substantial change in volume. Okay, any questions? Corinne.
So I entered in and I got 0.024. I didn't get that extra zero in between the 2 and the 4.
Maybe I messed up. Did anyone get an answer? Do we have a third opinion?
I could be wrong, but
I mean, so could I. I'm getting the same thing that I got before. Anybody else get something?
I'm getting the same thing you
I
got.
got the same thing.
Okay. I'm going to guess maybe when you were punching in the 1.013, maybe you missed a 0 or something. Or maybe missed a 0 on the 1.8 or I don't know. I think you're still getting the same thing, Corinne? 1.013 on top and 1.08 on the bottom. And 303 and 278. And then 0.02. That's curious. I don't know. Well, that might wind up being one of those mysteries that we can't solve. But so let's see. Carl got the same thing I got. Was there a third person who got what I got?
Yeah, I did.
I got the same thing as well.
Okay. All right. I think it must just be your calculator somehow. Okay. Let's try another one. So the next one is 16. Again, college physics 16.2. It says on a day when atmospheric pressure is 76 centimeters of mercury. So let me just write this down. It says centimeters of mercury, which would be the same as saying 760 millimeters of mercury, which is the same as 1 atmosphere. Okay. Just kind of filling it in for context. The pressure gauge on a tank reads the pressure inside to be 400 centimeters of mercury. So the gauge pressure is 400 centimeters of mercury. But we remember what the difference between gauge and the absolute pressure is. The gauge pressure is always, you have to add 1 atmosphere, or add the pressure outside to the gauge pressure to get the absolute pressure. So what this is saying is that the pressure inside is 400 centimeters of mercury bigger than the pressure outside. So the absolute pressure would be 476 centimeters of mercury, which is, well, I think we can leave it like that in this problem, because let's keep reading and see what it wants. It says the gas in the tank has a temperature of 9 degrees C. So the temperature equals 9 degrees C, which would be 272 Kelvin. And if the tank is heated to 31 degrees C by the sun, and if no gas exit, what will be the pressure inside? So this is kind of a T1, and there's a T2, which is 31 degrees C, and in Kelvin, that's going to be 304. We add 273 to 31, we're going to get 304. Okay, so this pressure that I called the absolute, we should just call that pressure 1. And then we want to know what pressure 2 is, but it technically says, what will the pressure gauge read? So we want to know the gauge pressure. The ideal gas law does not work with gauge pressure. Okay, just like it doesn't work with degrees Celsius. So this is almost like a little trick question. It looks like, let me show you, we want to do P1, well, let's put the 2's on top since we're looking for P2. P2 V2 equals NR T2, and P1 V1 equals NR times T1. We just stack the equations on top and we divide them. And the N's and R's have canceled. The volume of the tank doesn't change either, right? It's just a big metal tank. So its volume is barely going to change at all. If, you know, just tiniest change, we can ignore that. And so what we get is that P2 equals P1 times T2 over T1. So just see what happens. I'm going to do the wrong method first, okay? I want to make sure you see that. And that would be to just put in the 400 centimeters of mercury times 304 over 272 and see what we get. So don't even write the wrong approach down. We get 447 centimeters of mercury. Okay, so we might think, since we started with gauge pressure and they're asking us for gauge pressure, we could just use gauge pressure. But it doesn't work that way. So the right method would be to put in that 476 all right, I wrote 272. It should be 282. So let me correct the number. That was the wrong method for more reasons than I thought. Okay, so the wrong method really gives 431.2. Surprised none of you caught me on that one. Okay, so P2 is 513.1, and these guys are, what are they? They're centimeters of mercury, and the P2 gauge is going to be that value minus the atmospheric value, which is 437.1. You can see that when you do the wrong approach, the answer is not off by that much. And so it's not easy to realize you made a mistake because the answer, you know, it makes sense. Temperature goes up, the pressure goes up a little bit. And I can't tell whether, you know, before I see the number, whether, you know, 431 or 437 look better. Those are too close for me to be able to tell. So I'm just warning you about this, to be careful. When you see gauge pressures, or it doesn't say gauge pressure, but it says there's a pressure gauge, you have to think, Okay, convert everything to absolute pressure first, solve the problem, and then at the end, if it's asking you for the gauge pressure, you then have to go back to the gauge pressure. Okay, any questions about this problem? Okay, let's try one from the other book. And then we'll move on to something new. So this is from the 3000 Problems book, problem 20.15. It says use the general gas law, they mean the ideal gas law, to compute the density of methane, CH4, at 20 degrees C and 5 atmospheres of pressure. Okay, so we talked about this a little bit last time, that you can technically get the density from the ideal gas law. We have PV equals nRT. And what we want to do is somehow, use the number of moles to find the mass. Okay. Now this, it says, it doesn't say how many moles, so we can just sort of say, let n equal 1. And that could help us find the volume for 1 mole. And then we can find the mass of 1 mole. So to find the mass of 1 mole, we have to look up the values. Okay, so this is typically given. The molar mass of carbon is 12 grams per cubic centimeter. And for hydrogen, it's 1. So, for carbon, it's 12 grams per centimeter cubed. Grams per mole. I don't know why I'm saying grams per mole. And for hydrogen, it's 1 gram per mole. So altogether, we've got 1 carbon and 4 hydrogens. So that's 12 plus 4, 16 grams per mole. Okay, so if we say that we have 1 mole, our volume is nRT over P. We can put in 1 mole, and the volume of 1 mole is just going to be RT over the pressure. And the density is going to be the mass over the volume. So that's RT over pressure divided by the volume, or RT over the pressure times the volume. Okay. So let's work it out. The density would be R, that's 8.31. The temperature at 20 degrees C, remember we have to turn this into Kelvin, so that would be 293 Kelvin. The pressure is 5 atmospheres, so that's, to put that into pascals, we multiply 5 times 1.013 times 10 to the 5th. That's the number of pascals in 1 atmosphere. And then finally, we want to I messed up my formula here. What did I do? Mass over volume, so it's, I don't know what I'm doing. Mass over RT over P. So this should be mass times P over R times T. No, I just kind of goofed up my algebra there. Okay, let me re-put all these numbers. So the mass is 16 grams but I want to put it into kilograms. So that's 0.016 kilograms. And the pressure is 5 times 1.013 times 10 to the 5th. And R is 8.31, and the T is 293. Okay. Sorry about that. I don't know how I did that algebra so badly. It's going to be 3.33, and my units should be kilograms per cubic meter. I know my volume is going to come out in cubic meters if I made sure that my pressure is in pascals and my temperature is in Kelvin and so forth. And we deliberately put the mass into kilograms. Okay, so what if we, didn't sort of make this stretch? Let the number of moles equal 1. It doesn't tell us how much gas we have. So we basically can pick any number of moles we want and compute the volume of that number of moles and the mass of that number of moles. So it's easiest to get the mass of 1 mole. So, that's what I did. If we wanted to sort of work completely symbolically, we did this last time, but I'll show this to you again now that we've had a little more practice with the ideal gas law. The number of moles, or the molar mass, is equal to the total mass over the number of moles. So you take the total mass and divide by the number of moles. So the number of moles is equal to the total mass over the molar mass. So we could put that into the ideal gas law, PV equals nRT. That would be PV equals the mass of my gas over the molar mass times RT. And if we just rearrange this, we get M times P over R times T equals the mass over the volume, which is, the density. Okay, so you can kind of recover this formula with symbols first and not have to do this let n equals 1. But I kind of like just picking a number of moles, finding the mass of that number of moles, and then dividing that mass by the density. Okay, any questions? So you look like there's a question on the tip of your fingers. What's your question?
There was a problem in the book last week, and you emailed me about it, but what sort of situation would the R need to be in kilomoles versus just normal 8.31?
So if your number of moles is in kilomoles, then you could use the value of R in kilomoles. So it has to do with how many moles you have. When are you going to have kilomoles versus just moles? Generally, if you have kilograms of stuff, you're going to get kilomoles. And if you have just grams of stuff, you're going to get just moles. So generally, it's going to have to do with what numbers they gave you. If they say we had, 12 kilograms of nitrogen, then that's going to work out to be some number of kilomoles. But the real answer is you never need to use kilomoles. You can just take those kilograms and turn them into, find out how many moles there are in this many kilograms, and just use moles. I never use the kilomoles constant. So I would say If I were you, I would never use them. I would just convert everything into moles and then always use the same value of R.
Okay, thank you.
Sure. All right. So let's talk about something a little new. This is kind of a long thing. Let's see. I think maybe we'll break it into pieces. So what I want to do, this is now kind of some physics. What we have been doing is no different from what you might see in a chemistry class. But now we're going to try to get physical with it. So we're going to imagine we've got a box, and the box is full of air particles. Okay, and check out my perspective. I got lucky on that one. Okay, so we've got these particles just flying every which way they can go. Okay, just billions and billions and billions of particles. And we're going to try to come up with a sort of a microscopic description of the pressure that's based on, particles bouncing around and making collisions with the walls of this box and so forth. So we're going to get really kind of into the, just zoom in until we see individual particles bouncing around. And we're going to pick a little section of the wall with a certain area. And we're going to try to find how much force is going to be on that area, and therefore how much pressure we'll get. But not using the results from chemistry, not using the ideal gas law or any experimental results. This is just purely theoretical based on what we know about particles. So we're going to say, the pressure is going to be equal to the net force on the wall, or I guess I should say on the area, because it's not the whole wall, it's just a little area we chose. And then we're going to do some statistics to try to figure out, how many particles per second would be hitting that area. So the force is going to be, so the net force on the area is going to be broken into two pieces. We're going to kind of figure out two separate things. We're going to find the force per particle by just looking at a single particle and seeing what happens when a single particle with mass m and velocity v hits the wall. What happens? There's going to be a certain force given to the wall when this happens. And then we have to multiply this by the number of particles colliding with the wall in, some time interval. Okay, so we're breaking it in two pieces. The first part is kind of just physics. How much force does the particle give the wall when it hits and bounces off? And the second part is statistics. We want to know how many particles are going to hit that section, because most of the particles are going to hit other places. So let's focus first on the force per particle. We know that, let's break it into 2 bits. So here's my particle. It has a mass m and a velocity v, and it's going to hit the wall. And when it hits the wall, it's going to bounce off, and it's going to move, the opposite direction with a velocity minus v. I know that its velocity will be the same because it will be an elastic collision. And the wall is so massive that the wall doesn't really gain any kinetic energy from this collision, and so the particle must keep all of its kinetic energy. So whatever it started with, it has to have the same amount of kinetic energy. It's like a super ball bouncing off of the wall. It hits the wall, it bounces back, it's going just as fast when it bounces as it was coming in if it's perfectly elastic. So we could say that the net force on the particle would be the change in momentum over change in time. That's the momentum version of Newton's second law. So first I'm going to find the force on the particle, And then using Newton's third law, whatever's the force on the particle from the wall, the force on the wall from the particle must be the same amount, but in the opposite direction. So this is going to be P final minus P initial over delta T, and that would be M times minus V minus M times V. So my P final has a negative V, the way I drew my picture, and all of that is over delta T, and this just gives me a minus 2 mv over delta T. So that's the net force on the particle. But the net force on the wall is just minus the net force on the particle because of Newton's third law. So the net force on the wall is 2 mv over delta T. Okay, so that's the first part. We needed to know kind of the physics of a collision. When one particle hits the wall, it's going to put a little bit of force. Because the mass is so small, it's going to be a tiny force. But when we add up billions and billions of particles, it's going to wind up being, 100,000 newtons per square meter, the air pressure that we're currently enjoying. Okay, any questions about the force per particle part of this? All right, this is kind of a little bit of an intense thing here. So now we're going to go back and we're going to think about the number of particles that are colliding with this area. Okay, and what we're going to do is we're going to think of it as being a fraction of all the particles. So first of all, there's a few concerns. Some of the particles are not moving to the right, so they're not even going to hit that wall. So I want to exclude all the particles that are not going to hit that wall, that are not moving to the right. Some of the particles are moving to the right, but they're going to, they're going to hit down here. So they're going to miss my area. I want to exclude those particles as well. And then some of the particles are moving in the right direction. They're over here and they're on target, but we're going to be picking a very small time interval to do this calculation in. And these particles won't move far enough. They won't reach the wall in the time allowed. So let me copy this picture. I'm going to make it a little bit smaller so I have room to write stuff. So for the number of particles colliding, the number of particles colliding. So the number of particles colliding is going to be equal to the total number of the particles in the box. And then we're going to sort of fraction off stuff. So first of all, what fraction of the particles in the box are going to be moving to the right? So what fraction are going to be hitting this wall as opposed to one of the other surfaces? So how many surfaces are there on this box? How many walls are there? Well, maybe I shouldn't say walls. That's deceptive. How many surfaces that particles could hit?
Six?
Yeah, 6, right? Because it's kind of like a cube. There's 4 sides, and then there's the sort of the roof and the floor. So the particles, we would say that only 1/6 of the particles are even moving in the right direction so that they're going to encounter the wall in question. Okay? Now, we also want to exclude the particles that are missing the wall and that are too far away. So we define a little volume. Okay? And what we say is that the particles that are within this volume and that are moving to the right, okay, so only 1/6 of the particles in this volume will be moving to the right on average. But of these 1/6 of particles moving to the right, what only, they are going to hit this area, and anything that's beyond, that's over here, it's too far to hit, and anything that's down here is aiming at the wrong spot. So how do we determine how this, the details of this box? Well, there's a certain length of this box, and the length is determined by how far the particles can move in our time interval delta t. So the length would just be the velocity of the particles times delta t. It's kind of distance is velocity times time. So any particles that are farther away than the number dictated by this formula, they don't have enough time to reach the area. So here's the logic. I just want to pause and make sure everybody can catch this. This is the fine point. So just, shake off the, the slumber of long physics derivation. So here's the idea. If this little volume, I'm going to call it a V sub for a subset, like a subset of the total volume. If that's 1/10 of the total volume of the box, then we should be able to reason that 1/10 of the particles in the box are going to be located at any moment in time in this little scoring zone. This is sort of the scoring zone. We only want to count particles in here. So how many particles are in here? Well, it depends on the fraction, whatever fraction of the volume this is compared to the total volume. Again, if this is only 1/10 of the total volume, then we expect only 1/10 of the particles to be there. If this was 1/100th of the total volume, then only 100th of the particles will be there. And the way we get that fraction is just to divide the subvolume by the total volume. So by doing this next fraction I've added sort of slices off. If it's a 1-to-10 ratio, then we're going to have 1/10 of the total number of particles being in that box, and then we further divide by 6 to exclude all the particles in the little scoring zone that are moving the wrong direction. Okay, are you getting that logic? Any questions? Right, so what is my subvolume? It's just the area times the length of that box. And that would be 6 times the area times the velocity times delta t. Sorry, not 6 times the area. Area n times the area over 6 times capital V. Notice there's a little v in this formula for velocity and a big V for volume. So I'm making my big V kind of a bold Roman looking V so that I don't think that those cancel. Okay, those are different variables, the little v and the big V. So the pressure is going to be the net force on the area over the area. And the net force is the force per particle times the number colliding. And our force per particle was 2 mv over delta t. And my number of particles colliding is n area little v delta t over 6 big V. And all of this is divided by the area of my little section of the wall. So this is a theoretical microscopic description, and we can simplify it a lot. It's going to simplify a lot. So for example, the areas just cancel out. So that's good. As long as, I mean, the answer for pressure shouldn't depend on the area that we imagined, right? We just imagined an area. So that area cancels out. The delta t cancels out. as long as we make sure delta T is so small that we don't have to worry about particles that bounce around multiple times. Okay, if the particles can bounce back and forth multiple times and one particle can hit this area twice, then our statistics are all thrown off. But we just make sure that that time is very, very small, and then it crosses out. What else happens? There's a 2 over a 6. We can reduce that to a 1/3, and there's also a V and a V. So that's going to be a V squared. So putting it all together, what we get is a 1/3 M little v squared over big V. So this is a purely theoretical prediction of what the pressure in that box is going to look like based on the volume of the box, the masses of the particles, and the velocities of the particles. But if we rearrange this, we get PV equals 1/3 mv squared. And PV looks, well, looks like the ideal gas law, right? According to the ideal gas law, oh, I'm sorry, I'm missing my N. I'm missing my N. Okay, so PV reminds me of the ideal gas law. If we use the physics version of the ideal gas law, PV is equal to big N times K Boltzmann times T, and this is equal to 1/3 times big N times mv squared. So the big N just cancels out. It only works in the physics version. And now this is starting to look kind of provocative. 1/3 mv squared. Does that look familiar to you guys? 1/3 mv squared? It looks familiar. What does it look like, Corinne?
The kinetic energy 1/2 mv squared.
Yeah, it's almost the kinetic energy formula, right? So let's fix it. Let's make it 1/2 mv squared by factoring out a 2/3. Okay, you can see if I would multiply 1/2 mv squared times 2/3, that's going to get me back to 1/3 mv squared. So if I multiply both sides by 3/2, we get 3/2 K Boltzmann T equals 1/2 mv squared. Now that's really interesting because this is from a purely theoretical place. We just discovered that the temperature has a connection to the kinetic energy of the particles. Remember that historically, no one really knew what temperature was. They just said, hey, we just have some things that are hot and some things are cold. If I put them together, the heat flows from the hot one to the cold one. And we just made up this Fahrenheit scale to put things in order from hot to cold with no awareness of what exactly it was measuring. This shows us what it's measuring. This says, let me write it again. It says that this quantity, 3/2 times Boltzmann's constant times the temperature, is equal to the average kinetic energy of the particles in our gas. Okay, that is a huge, huge result because I asserted to you when we started talking about temperature that the modern understanding of temperature is it's measuring the average kinetic energy of the particles, but this is the proof. So this is known as the equipartition theorem. And after we come back from a break, we're going to talk about, what it means. But in the most simple terms, the basic idea, what it's telling us is that the temperature is a direct measurement of the kinetic energy of the particles. The rest of this stuff are just constants that essentially have to do with the units that we choose, because we didn't know when we invented temperature units that we should really be measuring them in joules. We should be measuring temperatures in joules because temperature is a measurement of average kinetic energy, but we don't. We measure them in Kelvin, and the Boltzmann's constant has to convert us from Kelvin into joules. So let me talk about the sort of interpretation of this and what we did that's correct and what we did that's not quite correct. So first of all, let's remember the Boltzmann constant. K Boltzmann is 1.38 times 10 to the negative 23 joules per Kelvin. So this is basically a conversion factor to take a Kelvin temperature and turn it into joules. That 3/2, there's a little bit of an interpretation to the 3/2. And I'm not going to get into that interpretation in this chapter. I'm going to mention it, and then we're going to return to it later. But we say that there is 1/2 K Boltzmann T per degree of freedom. Okay, so I'm going to kind of clarify that concept later when it becomes relevant to what we're doing. But essentially, that 3 came out of the fact that in our box, we can be moving in the X direction, the Y direction, or the Z direction. It came out of sort of the 6 sides of the box. And as we learn a little more, we're going to realize that there are other degrees of freedom, other ways that the particles can move, and that's going to modify this formula a little bit, okay? But I don't want to really delve into that this week. Just kind of keep it in the back burner of your mind. Essentially, though, all this really is saying, all this equation is saying is that what temperature does is it basically exactly measures the average kinetic energy of the particles. And as the temperature goes up, the average kinetic energy must go up. The 0 temperature corresponds with 0 average kinetic energy. No particles are moving at all in any way. So completely frozen. And that justifies our thinking of 0 degrees Kelvin as absolute 0, as the coldest things can get. We can never have less than 0 average kinetic energy. But when we did this calculation, we kind of made an assumption. We made a few assumptions that are not really legit. And I'm just going to point them out to you. So one thing we did is we assumed all of our particles are moving the same speed. And in reality, they're going to be moving different speeds. And we also assumed all of the particles have the same mass. But we know in a real box, there's probably going to be, you know, oxygen molecules and nitrogen and carbon dioxide, and, you know, all of those have different masses. So it turns out that this equation is correct for each kind of mass. So if you take all of the oxygen molecules in the room you're in, they are going to have the same average kinetic energy as all the nitrogen molecules. But because their masses are different, their velocities will be different. So we're gonna get into that in a minute. The second assumption we made is that the particles can either move north, south, east, west, up, or down, but we didn't have any particles kind of moving up at angles, going up at an angle from down here, and it hits the area and it bounces off. So, however, if we were to do the sort of full calculation, which would require calculus to sort of average over all of those different angular distributions and all the different velocity distributions of all the particles, we actually wind up with the same equation at the end. So this sort of simplified version gives us the flavor, it gives us the right result. The only thing to do is be careful about interpreting it. So we often want to say that this would allow us to find the velocities of the particles. Okay, we could rearrange this and try to solve for the velocity by canceling those 2's, multiplying by m, we get, or sorry, dividing by m, we get 3 K Boltzmann T over m equals v squared. Okay. Now the problem is that this velocity that appears here in the real world, there are lots of different velocities, and we have to average over all of those velocities. But when we average over the velocities, we get 0 because half of the particles are moving to the right and half of them are moving to the left. So we have to try to figure out a way to make sense of this. So what we do, we actually we square, if we do the real calculation, we wind up squaring the velocity and then finding the average of the square. Are you guys familiar with a bar over something to indicate an average? Have you seen that in math class? So this would indicate the average of the squares of the velocities. And if we take the square root of the average of the square of the velocity, we do not get the average velocity. We get something called RMS velocity. That stands for root mean squared. So the VRMS stands for the square root of the mean or average of the square of the velocity. And this is a concept that we'll see in the second semester as well. This idea of trying to average over something. If we average over it, because it's positive sometimes and negative sometimes, we get 0. And so we want to average its magnitude. So we square it. We average the square, and then we take the square root. So the RMS velocity is kind of like the average velocity, but it's not identical. It's kind of like the average speed. And the formula is 3k Boltzmann T over the mass of the particle. And what this does, it gives us a ballpark way of estimating the speed of particles. But again, the interpretation of what this is, the RMS velocity, it's not quite the same as the average speed. It's in the ballpark, though. I think it tends to be different by something like, under 10% from the average speed. But we have access to this. We don't have access to the average speed without doing a more fancy calculation. So let's go ahead and see how we could use this to find out how fast are, let's say, oxygen molecules in our room going. So this on the bottom is the number or the mass of one molecule. Now, we don't necessarily always have access to the mass of a single molecule. What we normally know is the mass of a mole of oxygen. That's the thing that's the number that's easy to look up. Lauren, do you have your hand up?
Yeah, I had a question. For the T, did you say it has to be in joules or kelvins? Like for the units?
What I said a while ago was we should measure it in joules, but we do measure it in Kelvin. And that's what the Boltzmann constant does, is it converts the joules into kelvins. Or the kelvins into joules, whichever way you use it. But yeah, when we use this formula, we're going to use Kelvin temperature. And the Boltzmann constant then kind of fixes up the units. So normally we can look up the molar mass or atomic mass of oxygen more easily than the mass of a single molecule. So it's kind of convenient. This is a little bit of a trick, is to multiply by Avogadro's number on the top and bottom. Because Avogadro's number times the mass of a single molecule gives you the molar mass. This thing here is just the molar mass. On the other hand, the Avogadro's number times the Boltzmann's constant multiplied together happens to be the ideal gas constant. So we can rewrite this formula as 3 times ideal gas constant R times T over the molar mass. And this is the form that is a little more useful. It's the same, it's going to give you the same number either way, but if we use this form, we can generally look up the molar mass more easily. So let's find the RMS for O2 at 25 degrees C and for H2 at 25 degrees C. So we have to know that these are diatomic. That should be stated in the problem. If you see this symbology, if you see an O with a little 2, that tells you it's diatomic. If you see the H with a little 2, it's diatomic. On the other hand, let's do helium also at 25 degrees C. So helium is not diatomic. It does not have that little 2. So we look these up. So the molar mass for O2, oxygen, if we go to the periodic table, has 16 grams per mole. But because it's diatomic, it's going to be 32 grams per mole, or 0.032 kilograms per mole. We want to put it into kilograms. The mass of H2, if we go to the periodic table, hydrogen has 1 gram per mole, but because it's diatomic, it will be 2 grams per mole. So 0.002 kilograms per mole. And the molar mass for helium is 4 grams per mole, and it's not diatomic, so we don't have to double that number. So that would be 0.004 kilograms per mole. Okay, the temperature, 25 degrees C converted to Kelvin, will be 298 Kelvin. And so let's do oxygen 2 first. The VRMS is going to be the square root of 3 times 8.31 times 298 over 0.032. We get 481.8 meters per second. So, that is a pretty good ballpark estimate of the average speed of oxygen molecules in, room temperature, 25 degrees C. If we compare that to H2, the top is the same, 3 times 8.31 times 298. The bottom is 0.02, and what we get is that this winds up being 4 times as fast, 1,927 meters per second. So hydrogen molecules at the same temperature are moving way faster than the oxygen molecules. Over time, the reason is, over time, these oxygen molecules and hydrogen molecules, they hit each other. And, they don't try to, those collisions start to equalize their kinetic energy just randomly, so that they wind up having the same average kinetic energy, but in order to do so, the hydrogen molecules have to move much faster. And for helium, put that a little lower. We have the square root of 3 times 8.31 times 298 and divided by 0.004. and that is 1,363. In fact that hydrogen and helium are moving so fast at room temperature results in us not having a whole lot of those gases in our atmosphere. In fact, the helium in our atmosphere is pretty much all gone. It's long since escaped from Earth, because if the average particle is moving this speed, it takes about 11,000 meters per second to escape from Earth, but there's a significant fraction of helium molecules at room temperature that bump up. So this is an average, but there's some that are high, and those particles escaped from our atmosphere. So even though helium is, probably the second most abundant element in the universe, on Earth, there's very little of it left. The only helium we have is basically trapped in underground caves, and people kind of harvest it. But we are actually now in a helium shortage. I don't know if any of you have ever tried to go get helium balloons in the last few years and been told, like, sorry, we're out of helium. But this happens all the time now because there's just not enough helium to go around, and a lot of medical research uses helium. And so that gets priority over party balloons. But, when you use balloons, you lose the helium and then it's gone forever. Hydrogen is not the same because, water has hydrogen. So we're always sort of dissociating water molecules and getting more hydrogen back in the atmosphere. But once it's in the atmosphere, it wants to leave as well. Okay, any questions? All right, that is it for this chapter. You should practice more. If you've been doing it already, good. If you haven't yet, start practicing the ideal gas law, and then you have a few questions on this VRMS stuff for today. And then on Thursday, we'll continue with this thermodynamic topic, but the material that we discussed Thursday will not be on your contest this coming Friday. So this is the last material that will be on the contest. It's going to be basically fluids, and what we've covered so far on heat, that would be basically temperature scales, thermal expansion, and ideal gas law, and then this VRMS stuff, finding the velocity of different gases at different temperatures. Going forward, we're going to start learning, now that we know that thermal energy is really just kinetic energy of particles, we're going to learn how can we take heat energy and convert it into useful work energy. That means we're going to learn how a steam engine, gasoline engine, and all of those things work, because this is the breakthrough we needed. This is the breakthrough we needed to realize that, hey, we can just burn stuff and take the heat produced when we burn stuff and turn that into useful work. Before this development, we couldn't make a steam engine or a gasoline engine, and we had and even still have a lot of stuff we can burn to sort of transform that energy into useful work, although it's getting more and more expensive and costly to do that. So we need other things as well. Anyway, that's what's coming, and that's going to be kind of some of the final material is to understand that process.